What if the solutions to some of our biggest modern challenges have been hiding in plain sight for thousands of years? Picture this. Civilizations long gone once possessed technologies so advanced, so ingenious, that they could still transform our world today. We often think of progress as a straight line moving forward. But what if history holds forgotten breakthroughs that could leapfrog us into a brighter future? From self-repairing materials to precision instruments that rival our own, the past is teeming with innovations that vanished, not because they failed, but because they were lost to time, war, or simply the chaos of history. Take a moment to consider how much knowledge has slipped through the cracks over centuries. The ancient Romans built concrete that heals its own cracks, a secret we've only just begun to rediscover. The Greeks designed astronomical devices so precise they could predict eclipses decades in advance. And in the Middle East, engineers crafted air conditioning systems that cooled entire buildings without a single watt of electricity. These weren't just lucky accidents, they were the result of brilliant minds working with the tools of their time, achieving feats that still leave us in awe. So why did these inventions disappear, and what could they teach us if we brought them back? That's exactly what we're about to uncover. In this journey through time, we'll explore 29 astonishing innovations from antiquity, each one a testament to human creativity, and each with the potential to reshape our future. Some were ahead of their time, others were tragically overlooked, but all of them hold lessons that could inspire new breakthroughs today. Whether you're a history buff, a tech enthusiast, or just someone who loves a good mystery, these lost marvels will make you question what we've been missing. So let's dive in, because the past might just be the key to unlocking tomorrow. To truly grasp the brilliance of these forgotten innovations, we need to step into the vibrant world of the civilizations that created them. Picture ancient Greece, where philosophers and inventors like Archimedes pondered the laws of nature while crafting machines that seemed to defy them. Or Rome, where engineers built roads and aqueducts so sturdy that some still stand today. Egypt's mastery of mathematics and medicine produced surgical tools eerily similar to modern instruments, while China's early experiments with paper and gunpowder laid foundations for entire industries. And in Mesopotamia, the cradle of civilization, astronomers tracked celestial movements with astonishing precision. These weren't primitive societies, they were hubs of ingenuity, where curiosity and necessity collided to spark revolutions in technology. Yet despite their achievements, so much of their knowledge vanished. Why? Sometimes it was the chaos of war, like the burning of the Library of Alexandria, where countless scrolls were lost forever. Other times, innovations were guarded as state secrets, like China's silk production, which remained a mystery to the outside world for centuries. And then there's the slow erosion of time. Ideas passed down orally or written on fragile materials that simply crumbled away. But perhaps the most tragic loss wasn't the inventions themselves, but the mindset behind them, a willingness to experiment, to fail, and to push boundaries without the constraints of modern specialization. Rediscovering these innovations isn't just about unearthing old gadgets, it's about reclaiming a way of thinking. Imagine if we combined today's resources with the bold creativity of antiquity. What could we achieve? That's the real power of looking backward, not to copy the past, but to ignite new possibilities for the future. Buried beneath the waves for 2,000 years, the Antikythera Mechanism emerged from a shipwreck as one of history's most baffling puzzles. Discovered off the coast of Greece in 1901, this corroded bronze artifact seemed unremarkable at first, until researchers realized it housed a labyrinth of interlocking gears, each precisely calibrated to mirror the movements of the cosmos. Imagine a device no larger than a shoebox, capable of tracking the cycles of the moon, predicting solar eclipses, and even accounting for the irregular orbit of planets, all without electricity, microchips, or modern engineering. This wasn't just a tool, it was a miniature universe in motion, crafted with a level of sophistication that wouldn't reappear until the Industrial Revolution. What makes the Antikythera mechanism so extraordinary isn't just its complexity, it's the sheer audacity of the thinking behind it. Ancient Greek astronomers didn't merely observe the stars, they sought to replicate their dance mechanically, translating abstract celestial patterns into tangible, turning gears. The device even accounted for subtle anomalies like the elliptical paths of planets, a concept formalized by Kepler centuries later. Modern X-ray scans reveal layers of craftsmanship that defy expectations: differential gears, a lunar phase display, and a dial tracking the 4-year cycle of the Olympic Games. This wasn't trial and error. It was precision engineering, likely born from a collaboration between astronomers, mathematicians, and master metalworkers. Yet here's the haunting question: why did such groundbreaking technology vanish without a trace? The Antikythera mechanism stands alone, with no surviving predecessors or successors. Historians speculate that the knowledge may have been concentrated in a single workshop, lost when war or disaster struck, or perhaps the device was so advanced that only a handful of scholars understood its workings, and their expertise died with them. Whatever the reason, its rediscovery forces us to reconsider the trajectory of human innovation. We assume progress is linear, but the Antikythera mechanism suggests that brilliance can flare up, fade away, and wait centuries to be rekindled. Today, engineers are studying its design for clues that could revolutionize modern robotics. The Greeks achieved accuracy without digital sensors or brittle materials, relying instead on elegant, durable gear trains that endured saltwater and millennia. In an age where we're obsessed with miniaturization and sustainability, the Antikythera mechanism whispers a counterintuitive lesson. Sometimes, the most advanced solutions aren't the newest but the wisest. What other secrets might still lie hidden in the ashes of antiquity, waiting to spark the next leap forward? While modern concrete cracks and crumbles under pressure, the Pantheon's dome has defied time for 2 millennia, standing tall, unshaken, even as empires rose and fell around it. What's the secret behind this ancient supermaterial? The answer lies in a recipe so ingenious, scientists are only now beginning to decode its magic. Roman engineers didn't just mix sand and water, they blended volcanic ash from the hills of Pozzuoli with lime and seawater, creating a chemical reaction that transformed ordinary mortar into something extraordinary. Over time, tiny cracks in their structures didn't spell disaster, they triggered a self-repairing process. As seawater seeped in, it reacted with the ash to form new minerals, knitting the gaps back together like invisible stitches. This wasn't just durable concrete, it was concrete that grew stronger with age. Today's engineers are racing to replicate this ancient alchemy. Modern concrete, reliant on Portland cement, is brittle by comparison, prone to crumbling within decades, especially in harsh coastal environments. But imagine infusing our cities with Roman-inspired materials that heal themselves, slashing maintenance costs and reducing the carbon footprint of constant repairs. Researchers at MIT and Berkeley have already made strides, testing volcanic ash substitutes and even introducing bacteria that mimic the Pantheon's self-healing properties. The irony is striking. While we've spent centuries refining concrete, the Romans might have already perfected it. Their recipe wasn't just about strength, it was about harmony with nature, using local materials and embracing the elements instead of fighting them. Yet the real lesson here isn't just chemical, it's philosophical. The Romans built for eternity, prioritizing longevity over quick fixes. In an era of disposable infrastructure, their approach feels revolutionary. What if we stopped designing bridges and buildings with expiration dates? The Pantheon's resilience whispers a challenge across the centuries. Durability isn't about reinventing the wheel. Sometimes it's about rediscovering it. As rising sea levels and extreme weather test our modern cities, the past might hold the blueprint for a more resilient future, one where our constructions don't just endure but evolve. Few weapons in history have inspired as much awe or as much frustration as Greek fire. Picture this: Byzantine ships surrounded by enemy fleets unleash a fiery liquid that clings to everything it touches, burning relentlessly even on water. Flames leap from vessel to vessel, turning the sea itself into a blazing inferno. This wasn't just a weapon, it was a psychological terror, a technological edge so devastating that it kept Constantinople safe for centuries. The secret of its composition was guarded like a state treasure, passed down only to emperors and trusted alchemists. And when the city finally fell in 1453, the knowledge vanished, leaving behind only cryptic descriptions and the lingering question: what made Greek fire so unstoppable? The mystery begins with its properties. Historical accounts describe a liquid that ignited on contact with water, impossible to extinguish with ordinary methods. Some scholars believe it contained quicklime, which reacts violently with moisture, while others point to petroleum or naphtha distilled from crude oil resources the Byzantines accessed near the Black Sea. What's clear is that this wasn't just thrown together. It was a carefully engineered substance, likely pressurized and sprayed through bronze tubes mounted on ships. The effect was like a medieval flamethrower, capable of projecting fire dozens of feet with terrifying precision. Modern scientists and historians have tried for decades to crack the code, with tantalizing near misses. In the 1960s, a chemist proposed a mix of pine resin, sulfur, and calcium phosphide, which reacts with water to produce flammable gas. More recent experiments suggest a combination of crude oil, saltpeter, and even animal fats to create a sticky, slow-burning gel. Yet no recreation has fully matched the historical descriptions. The Byzantines may have used ingredients or techniques we've overlooked, perhaps a rare mineral or a forgotten distillation method. But here's the twist. The real value of Greek fire today might not lie in its destructive power, but in what it could teach us about energy. Its ability to burn on water hints at chemical reactions we're still struggling to harness, like controlled combustion for clean fuel or emergency flares that work in monsoons. Even its delivery system, those pressurized nozzles, could inspire more efficient ways to disperse fire retardants or liquid fuels in extreme conditions. The Byzantines didn't just create a weapon, they stumbled onto principles of chemistry and fluid dynamics that we're still unpacking. The loss of Greek fire is a stark reminder of how fragile knowledge can be. One empire's obsession with secrecy became history's loss, leaving us to piece together fragments of a technology that could have accelerated science by centuries. Yet its legend endures, challenging us to ask, how many other ancient breakthroughs are waiting to be rediscovered, not in dusty manuscripts, but in the very way we approach modern problems? Sometimes progress doesn't mean inventing something new, it means remembering what we've forgotten. In the hands of a skilled warrior, a Damascus steel sword could slice through a silk scarf drifting in midair or cleave an enemy's helmet without losing its edge. These legendary blades, forged in the Middle East between the 3rd and 17th centuries, weren't just weapons, they were masterpieces of metallurgy, combining razor-sharp durability with a mesmerizing wavy pattern that shimmered like flowing water. Yet by the 18th century, the secrets of their creation had vanished, leaving behind only scattered blades and frustrated scientists. What made this steel so extraordinary? And why, despite centuries of effort, has no one fully replicated its magic? The answer lies in a perfect storm of geology and craftsmanship. Original Damascus steel wasn't just iron and carbon. It began as wood steel, a high-purity alloy imported from India and Sri Lanka, rich in trace elements like vanadium, molybdenum, and even traces of rare metals from ancient mines. But the real alchemy happened in the forge. Blacksmiths heated, folded, and hammered the metal in precise cycles, creating microscopic layers of cementite, a super-hard compound, woven into a flexible matrix of softer steel. This structure gave the blades their signature toughness. They could bend without breaking, hold an edge sharper than modern scalpels, and even self-sharpen as tiny layers wore away during use. Modern electron microscopes reveal carbon nanotubes embedded in some surviving blades, a nanostructure we're only now learning to engineer intentionally. Yet the technique's disappearance remains a cautionary tale. Some historians blame the exhaustion of those critical Indian ore deposits, while others point to the rise of firearms, which made sword-making a dying art. But the most intriguing theory involves the oral traditions behind the craft. Like chefs guarding a secret recipe, master smiths passed down their knowledge through apprenticeships, never writing it down. When political upheavals or plagues disrupted these chains, the expertise evaporated. Today, materials scientists are closer than ever to cracking the code. Laboratories use spectroscopy to analyze ancient blades atom by atom, while blacksmiths experiment with vanadium-infused alloys and rapid cooling techniques. The potential applications stretch far beyond swords. Imagine turbine blades that resist fatigue, surgical tools that stay sharper longer, or even earthquake-resistant building materials inspired by that layered flexibility. The irony, we're spending millions to reverse engineer what medieval craftsmen achieved with charcoal fires and hammers. Damascus steel reminds us that innovation isn't just about inventing, it's about preserving. In our rush toward the future, we've lost techniques that could solve modern problems with ancient wisdom. Perhaps the real challenge isn't recreating the steel, but rebuilding the culture that nurtured such mastery. One where patience, observation, and deep respect for materials were as vital as the tools themselves. In a quiet corner of the Baghdad Museum sits an unassuming clay jar, no taller than a coffee mug, but inside lies a puzzle that could rewrite the history of technology. Dated to around 200 BCE, this artifact contains a copper cylinder wrapped around an iron rod, all sealed with a mysterious asphalt-like substance. When filled with an acidic liquid like vinegar or grape juice, something extraordinary happens. It generates electricity, not enough to power a city, but a measurable current similar to a basic modern battery. This isn't science fiction. It's the Baghdad Battery, a 2,000-year-old enigma that forces us to ask, were ancient Mesopotamians harnessing electricity centuries before the term was even coined? The implications are staggering. Recreations by researchers like Willard Gray in the 1930s confirmed the jar could produce around 1 volt of electricity, enough for small-scale electroplating or even medicinal purposes. Some speculate that similar devices might have been used to gild statues with thin layers of gold, a technique known in ancient Egypt and Mesopotamia. Others suggest more esoteric applications, like temple rituals where worshippers touch the device to experience a tingling, divine shock. But here's the catch: no wires, no switches, no other electrical artifacts have been found alongside it. The Baghdad Battery stands alone, a tantalizing what-if without a clear paper trail. Critics argue it might have been a storage vessel for sacred scrolls, the iron rod merely a rusted support. Yet the design is suspiciously efficient for generating current. The copper acts as a positive terminal, the iron as a negative, and the asphalt seals the components while resisting corrosion, a level of precision that feels intentional. Even more intriguing are ancient texts that hint at knowledge we've overlooked. The Parthians who ruled Baghdad at the time described magical jars that could hold lightning, while Egyptian carvings show bulb-like objects with snaking filaments, though mainstream archaeology dismisses them as symbolic art. What if the Baghdad battery wasn't a fluke, but a glimpse into a lost branch of science? Imagine a world where early experiments with electricity weren't snuffed out by time, but nurtured. Could the Industrial Revolution have arrived 1,000 years earlier? While we'll never know for certain, the artifact's real value lies in the questions it forces us to confront. Our ancestors weren't just stumbling in the dark, they were probing the boundaries of their world with tools we're only beginning to understand. Today, engineers study the Baghdad battery not to replicate it, but to appreciate how innovation can emerge from the humblest materials. In an era obsessed with high-tech solutions, this ancient jar whispers a quiet lesson. Sometimes, the simplest ideas hold the most spark. Imagine standing in the imperial court of ancient China in the year 132, when suddenly, a bronze dragon perched on an ornate vessel opens its mouth and a metal ball drops straight into the waiting mouth of a toad below. This wasn't theater, it was the world's first earthquake detector, and it had just sensed a tremor hundreds of miles away. Invented by polymath Zhang Heng, this ingenious device, known as the Hufeng Didongi, didn't just detect quakes, it pointed to their origin with uncanny accuracy, all without a single gear or electronic sensor. The secret lay in its elegant simplicity. The seismoscope was a bronze urn adorned with 8 dragons, each facing a cardinal direction with corresponding toads at the base. Inside, a pendulum hung delicately, balanced to remain still during minor vibrations but swing dramatically when seismic waves struck. The direction of the swing would trigger a mechanism, likely a lever or tilted rod, that released a ball from the dragon's mouth closest to the quake's epicenter. One account describes it detecting a distant earthquake the court hadn't even felt, only for messengers to later confirm the tremor in the exact direction the device indicated. Modern engineers are still unraveling how Zhang Heng achieved such precision with ancient materials. Some theories suggest the urn contained a system of inverted pendulums or weighted arms tuned to specific frequencies of seismic waves. Others propose it used a liquid-filled chamber to amplify subtle movements. What's undeniable is its sophistication. While early European seismographs wouldn't appear until the 1800s, this design combined mechanics, geology, and artistry in a way that feels almost futuristic. Today, researchers see potential in Zhang Heng's approach for disaster prevention. Modern seismographs rely on networks of sensitive electronics, but they're expensive and vulnerable to power outages. The seismoscope's passive design, requiring no external energy, could inspire backup systems for remote regions or even space missions where electricity is scarce. Scientists in China and Italy have built working replicas, testing their responsiveness to simulated quakes. The results surprisingly effective, especially for a 2,000-year-old concept. But the real lesson isn't just technical, it's philosophical. Zhang Heng's device embodies a holistic view of science where beauty and function intertwine. In an era obsessed with digital complexity, his seismoscope whispers a reminder: sometimes the most elegant solutions emerge not from adding parts, but from understanding the world's natural rhythms. As we face rising seismic threats from climate change and urban expansion, perhaps the past holds keys to sensing the Earth's whispers before they become roars. One of the most mesmerizing artifacts from antiquity sits quietly in the British Museum, defying expectations with every shift of light. The Lycurgus cup, crafted in 4th century Rome, isn't just a masterpiece of glasswork, it's a scientific marvel. Under normal light, it glows a deep jade green, but illuminated from within, and the glass transforms into a radiant ruby red. This isn't magic, it's nanotechnology, achieved over 1,500 years before the term even existed. The secret: ancient artisans infused the glass with infinitesimal particles of gold and silver, ground so finely that they measure just 50 nanometers across, smaller than a wavelength of light. At this scale, the particles interact with light in extraordinary ways, scattering blue and green wavelengths while allowing red to pass through. The effect, called dichroism, is so precise that modern scientists struggle to replicate it without advanced equipment. How did Roman craftsmen achieve such precision without microscopes or chemistry labs? The answer lies in a blend of artistry and accidental discovery. Historians believe they added gold dust and silver salts to molten glass, then carefully reheated and cooled it, unknowingly creating nanoparticles through controlled oxidation. Some theories suggest they borrowed techniques from Egyptian glassmakers, who'd been experimenting with metal-infused glazes for centuries, but the Lycurgus cup stands alone in its sophistication, hinting at a level of empirical understanding that borders on the uncanny. These artisans didn't just stumble upon a pretty effect, they refined it, mastering ratios and temperatures to produce consistent results. Today, material scientists are mining these ancient methods for cutting-edge applications. The cup's color-shifting properties rely on the same principles used in modern photonic crystals, which manipulate light for everything from solar panels to medical sensors. Researchers at the University of Illinois have even explored using similar nanoparticle dispersions to create ultra-secure anti-counterfeiting inks or smart windows that adjust transparency based on sunlight. But here's the twist. While we chase these innovations with billion-dollar labs, the Lycurgus cup suggests that low-tech, observation-driven experimentation might hold untapped potential. Its creators didn't understand quantum physics, but they observed, tinkered, and perfected, a reminder that breakthroughs don't always require blueprints. The cup's true mystery isn't just how it was made, but why the knowledge vanished. By the Middle Ages, the technique had faded into legend, leaving later glassmakers to regard it as alchemy. Was it a trade secret too closely guarded, a casualty of Rome's decline? Whatever the reason, its rediscovery challenges our assumptions about progress. We assume older means primitive, yet the Lycurgus cup whispers a different story. That ancient craft and modern science might not be so far apart after all. In a world obsessed with pushing forward, sometimes the most revolutionary ideas are the ones we forgot. High in the Andes, the Inca Empire thrived without a traditional written language, yet they built one of history's most sophisticated administrative systems using nothing but strings and knots. These weren't just ropes, they were quipus, intricate devices where every twist, color, and position held meaning. Picture a cascade of cords, some as short as a finger, others stretching longer than a person, each threaded with precise clusters of knots. To the untrained eye, they might resemble macrame art, but to Inca record keepers, they encoded everything from tax records to sacred stories, all without a single written word. What makes Quipus so extraordinary is their complexity. Main cords served as anchors, with pendant strings branching off like a family tree. The type of knot, whether a simple overhand or an elaborate figure 8, could signify numbers, while their placement along the string indicated place values, creating a base 10 system rivaling modern spreadsheets. Colors added another layer. Crimson might denote warriors, gold for tribute, white for peace. Some scholars believe certain quipus even recorded historical events or astronomical cycles, turning them into tactile libraries. But here's the mystery: despite decades of study, we've only cracked part of the code. Of the roughly 1,000 surviving quipus, most align with numerical accounts, but a handful defy explanation. They're knots arranged in patterns that hint at narratives or even poetry. Could these be the lost epics of the Inca, waiting to be read? Modern researchers are racing to decode them using AI and 3D imaging, treating each knot like a pixel in a larger message. The potential parallels to computing are startling. Quipus operate like a physical binary system, where knots represent on and blank spaces off, a precursor to the ones and zeros that power our digital world. Some theorists speculate they could inspire new forms of durable, low-tech data storage, ideal for preserving information in extreme environments where hard drives fail. Imagine disaster-proof archives woven into cords, or educational tools that blend math with tactile learning. Yet the greatest lesson of Quipus might be about accessibility. Unlike ancient scripts requiring years of study, these knots could be read by touch, making them inclusive for those who couldn't see. In a world drowning in digital noise, their silent elegance whispers a question. What if the next breakthrough in communication isn't about building faster chips, but rediscovering the wisdom of simplicity? The Inca didn't just record data, they wove it into something lasting, flexible, and alive. Legend has it that during the siege of Syracuse in 212 BCE, the brilliant Archimedes lined up a series of polished bronze mirrors along the city walls, angling them to concentrate sunlight into a single, searing beam. As Roman ships approached, their wooden hulls suddenly burst into flames, incinerated by what amounted to the ancient world's most terrifying magnifying glass. Historians have debated this tale for centuries. Was it fact, exaggeration, or pure myth? But here's what's fascinating. Modern scientists have put the concept to the test, and the results are startlingly convincing. In 2005, a team from MIT recreated the so-called Archimedes death ray using just 127 mirrored panels, each about the size of a classroom whiteboard. When focused on a wooden ship replica 200 feet away, flames erupted within seconds. A later experiment by the TV show Mythbusters achieved similar results, though they noted the challenge of maintaining precise alignment on moving ships. The conclusion: while the historical accuracy remains unproven, the physics is undeniably sound. Archimedes, a man who calculated pi and invented the water screw, certainly had the geometric expertise to pull it off if he'd chosen to. But the real magic of this story isn't about ancient warfare. It's about the untapped potential lurking in old ideas. Today, concentrated solar power plants use the same basic principle on an industrial scale, with vast arrays of mirrors, called heliostats, directing sunlight toward central towers to generate steam and electricity. Some facilities, like the Ivanpah plant in California, can produce enough energy to power 140,000 homes, all by harnessing sunlight the way Archimedes might have imagined. Researchers are even exploring smaller-scale applications, like portable solar concentrators for off-grid desalination or emergency medicine sterilization in remote areas. What makes Archimedes' concept so enduring is its elegant simplicity. Unlike complex machinery, mirrored surfaces require no rare materials or advanced engineering, just precise geometry and an understanding of light. In an era grappling with climate change, that's a potent reminder. Sometimes the greenest solutions aren't the newest, but the wisest ones we forgot. The next breakthrough in renewable energy might not come from a lab, but from a 2,000-year-old idea waiting to be polished anew. In the scorching deserts of ancient Persia, architects confronted a challenge we still grapple with today: how to keep cool without draining precious resources. Their solution, the windcatcher, a towering structure that harnessed nature's own rhythms to transform sweltering interiors into oases of relief. Picture a series of tall, chimney-like towers rising above clay rooftops, their slatted openings strategically angled to catch even the faintest breeze. As wind flowed downward, it passed over subterranean water channels or cool earthen walls, dropping the temperature by as much as 20 degrees before circulating through homes. No electricity, no moving parts, just pure, ingenious physics. What makes these 2,000-year-old designs so remarkable is their adaptability. In Yazd, Iran, windcatchers varied by neighborhood. Some scooped airflow from all directions, while others targeted seasonal winds. The tallest could reach 60 feet, funneling air deep into communal spaces or even underground icehouses where perishables were stored year-round. But the real magic lay in their bidirectional flow. At night, the process reversed. Warm indoor air rose through the towers, drawing cooler night air inside like a natural vacuum. This wasn't just air conditioning. It was a self-regulating climate system, finely tuned to the DESERT's Chinese letter rhythms. Fast forward to today, and engineers are revisiting these concepts with fresh urgency. A study by the University of Cambridge found that modern adaptations of windcatchers could slash cooling energy use by up to 90% in arid regions. Architects from Dubai to Arizona are experimenting with hybrid designs, combining traditional tower shapes with solar-powered fans for consistent airflow. Even museums are getting in on the act. The Masdar City complex in Abu Dhabi features windcatchers that reduce its reliance on conventional AC by 40%. The irony: we're spending billions on high-tech solutions when the past already holds a blueprint for sustainable comfort. Yet the windcatcher's legacy isn't just about temperature control. It's a masterclass in biomimicry, a reminder that the best designs often mirror nature's simplicity. Unlike energy-guzzling air conditioners, which isolate us from our environment, these towers worked in harmony with wind patterns, topography, and even the Earth's thermal mass. In an age of climate crises, that philosophy feels revolutionary. What if our buildings didn't fight the elements but danced with them? The answer might not lie in the next breakthrough material, but in the quiet wisdom of towers that have stood the test of time and heat. Rising 23 feet above Delhi's Quip complex, the Iron Pillar has baffled scientists for generations. While modern steel bridges and skyscrapers succumb to rust within decades, this 1,600-year-old monument remains pristine, its surface smooth and uncorrupted by time. The secret: a blend of metallurgical genius and accidental chemistry that ancient Indian smiths perfected centuries before the scientific method existed. At first glance, the pillar's composition seems straightforward, over 98% pure wrought iron, but it's the remaining 2% that holds the key. Unlike contemporary alloys that rely on chromium for rust resistance, this artifact contains unusually high phosphorus levels, nearly 1%, alongside traces of sulfur. These impurities, typically considered flaws in modern metallurgy, form an astonishingly thin protective layer called mesowite. Just nanometers thick, this film acts like an invisible shield, repelling moisture and oxygen that would otherwise eat away at the metal. Even more remarkable, the phosphorus wasn't added intentionally. It came from the unique smelting process. Ancient furnaces used charcoal from high phosphorus iron ores, and the artisan's hammering technique distributed the element evenly, creating a homogeneous barrier no modern factory could replicate without precise lab conditions. Recent studies at the Indian Institute of Technology revealed another layer of sophistication. The pillar's surface develops this protective coating over time through a reaction with Delhi's climate, meaning its rust-proofing isn't static but adaptive. In humid monsoon seasons, the phosphorus-rich layer thickens slightly, then stabilizes during dry spells. This self-regulating property mirrors modern, smart materials designed to respond to environmental changes, yet it was achieved through empirical craftsmanship alone. The implications for today's engineering are profound. Corrosion costs the global economy over $2 trillion annually, from crumbling infrastructure to weakened ship hulls. While we can't replicate the pillar's exact composition, its phosphorus content would make most modern alloys brittle. Researchers are experimenting with phosphorus-doped steel coatings for bridges and offshore platforms. Some even speculate that the ancient slow, labor-intensive forging process, which allowed crystalline structures to align perfectly, might hold clues for 3D printed metals that resist fatigue. Yet the pillar's greatest mystery isn't technical, it's cultural. How did this knowledge vanish? Unlike Damascus steel or Roman concrete, India's ironworking traditions survived well into the medieval period, with texts like the 12th century Rasaratna Samuchaya detailing advanced metallurgy. Perhaps the answer lies in shifting priorities. As empires fell and warfare evolved, the painstaking methods behind such monuments gave way to mass production. Today, the pillar stands not just as a testament to forgotten science, but to the delicate balance between artistry and progress, a reminder that some breakthroughs aren't lost because they fail, but because we stop valuing the patience they demand. While modern astronomers rely on satellites and supercomputers, the Maya mapped the cosmos with nothing more than naked eye observations and stone-carved records, and their precision would put many of our tools to shame. Take their tracking of Venus, the dazzling evening star that dominated their celestial mythology. Using nothing but aligned sightlines in observatories like El Caracol at Chichen Itza, Maya priests calculated Venus' 584-day synodic cycle with an error margin of just 2 hours, a 99% accuracy rate. This wasn't guesswork, it was the result of generations of meticulous record-keeping, etched into bark paper codices and temple walls with a mathematician's rigor. What makes their achievements even more astonishing is the context. Unlike the Greeks, who used geometry to model planetary motion, the Maya approached the heavens through cyclical time. Their famed long count calendar didn't just track days, it interwove Venus movements with solar years and lunar months into a grand cosmic clock. At the Dresden Codex, a surviving Maya manuscript, tables predict Venus positions 50 years in advance, correcting for celestial drift with a sophistication rivaling modern ephemerides. They even accounted for the planet's irregular appearances, dividing its cycle into 4 phases tied to warfare and agriculture. When Venus rose as the morning star, it signaled time for planting. As the evening star, it foretold conflict. This wasn't just astronomy, it was a seamless fusion of science, spirituality, and survival. Modern researchers are still unraveling their methods. At Capon's Temple of the Inscriptions, archaeologists found sightlines where rulers marked Venus extremes, its northernmost and southernmost risings using notches in stone. Other sites feature E-groups, architectural arrangements where pyramids and platforms align with solstices and Venusian events. But the real breakthrough came when scholars realized the Maya compensated for observational error through redundancy. By cross-referencing multiple cycles like the 8 solar years that nearly equal 5 Venus cycles, they created self-correcting algorithms. It's as if they'd invented an ancient spreadsheet, using stone and starlight instead of silicon. So what can their legacy teach us today? Surprisingly, a lot. In an age of GPS, we've lost the art of celestial navigation, a skill the Maya perfected. Their emphasis on long-term cycles also offers a counterpoint to our short-term thinking. Where we see randomness, they detected patterns spanning centuries. NASA engineers have even studied Maya math to improve deep space mission scheduling, proving that sometimes the oldest ideas are the most timeless. The Maya didn't just watch the stars, they conversed with them, leaving behind a challenge to see the universe not as a void to conquer, but a rhythm to join. 2,000 years before James Watt refined the steam engine, a brilliant mind in 1st century Alexandria had already unlocked its basic principles, then treated it as little more than a party trick. Hero of Alexandria's Eolipile was a deceptively simple device, a hollow metal sphere mounted on pipes, filled with water and suspended over a fire. As steam built inside, it escaped through 2 bent nozzles, causing the sphere to spin wildly, a rudimentary turbine demonstrating the power of steam propulsion. This wasn't just a curiosity, it was the seed of an industrial revolution that never took root. So why did this groundbreaking invention end up as a temple marvel rather than a world-changing machine? The answer lies in the gap between invention and application. Heroes' design, while ingenious, emerged in a society with no pressing need for mechanized labor. The Mediterranean world of his time thrived on abundant enslaved workers and animal power, making steam technology seem like an extravagant novelty rather than a practical solution. Without the economic pressures that later drove 18th century Britain coal mines flooding, textile demand exploding, there was little incentive to scale the Eolipile beyond theatrical demonstrations. Hero himself catalogued it among pneumatic wonders like automatic temple doors and coin-operated holy water dispensers, more concerned with spectacle than industry. Yet the lost potential is staggering. Modern engineers have recreated Hero's device, revealing it could have generated meaningful rotational force if connected to gears or pulleys. Imagine if Alexandrian scholars had paired it with the water wheels and crank mechanisms already known to the Romans. Could they have built steam-powered mills or ships? The metallurgy of the era might have limited pressure tolerance, but historians note that Byzantine bellows could reach temperatures high enough for basic steam engines. The pieces were there, they just never clicked into place. What's most poignant is how close the ancient world came to glimpsing the future. Chinese inventors later developed steam-powered toys, and Ottoman scholars studied Hero's texts, yet no culture industrialized the concept. The Eolipile story isn't one of failure, but of context. Innovation needs more than brilliance. It needs a society ready to embrace it. Today, as we face challenges like climate change, Hero's forgotten turbine whispers a warning. Breakthroughs aren't enough. We must cultivate the vision to recognize them. Perhaps the next world-changing idea isn't waiting to be invented, but to be seen, truly seen, for what it could become. When we think of ancient armor, gleaming metal plates or tough leather come to mind. But what if one of history's most effective defenses was made from something as humble as paper? During China's Tang dynasty, warriors donned armor crafted from laminated paper, layer upon layer pressed and treated to create a material that could stop arrows in their tracks. This wasn't makeshift protection. It was a carefully engineered solution, lighter than metal yet astonishingly resilient. Tests with historical replicas show that properly layered paper armor could absorb the impact of arrows just as well as heavier alternatives, while allowing unmatched freedom of movement. The secret lay in its construction, Up to 15 sheets of mulberry or hemp paper bonded with resin or lacquer, then quilted into a flexible vest, the result. A material that dispersed force across its fibers, turning a lethal strike into a survivable one. What's fascinating is how this innovation emerged from necessity. Paper, invented in China around the 2nd century BCE, was abundant and cheap compared to scarce metals. But its transformation into armor wasn't just about thrift, it reflected deep understanding of material science. Artisans exploited paper's natural properties. Its fibrous structure created a web of tension, while the laminations added thickness without rigidity. Some versions even incorporated silk threading for extra reinforcement, creating a composite material centuries before the term existed. And unlike metal, which could rust or become brittle in cold weather, paper armor resisted moisture when treated properly, making it ideal for diverse climates. Modern researchers are now asking, could this ancient idea inspire the next generation of protective gear? Today's body armor often relies on synthetic fibers like Kevlar, which, while effective, can be heavy and expensive to produce. But experiments blending traditional paper-making techniques with nanomaterials hint at exciting possibilities. Scientists in Japan and Germany have developed ultra-lightweight shields using cellulose nanofibers, a high-tech cousin of Tang Dynasty paper, that outperforms steel in some impact tests. Others are exploring layered graphene paper composites that could offer flexibility and strength beyond current standards. The irony is palpable. We're spending millions on futuristic materials, while the past holds a blueprint we've barely tapped. Beyond armor, the implications stretch into everyday design. Imagine car interiors with paper-based impact zones, or disaster shelters built from laminated panels that are both lightweight and crush-resistant. Architects are already testing paper-derived materials for temporary housing, noting their sustainability and low carbon footprint. The Tang Dynasty's innovation reminds us that advanced solutions don't always require complex chemistry. Sometimes they're hiding in plain sight, waiting for us to see their potential anew. In a world obsessed with high-tech answers, perhaps the next breakthrough will come not from a lab, but from a page in history. Among the dust of Pompeii's ruins and scattered across former Roman military outposts, archaeologists keep uncovering something startling: gleaming bronze and iron instruments that could pass for modern surgical tools. Delicate scalpels with replaceable blades, precise bone drills with fluted tips to reduce friction, even specialized forceps for extracting arrowheads or stitching wounds. These weren't crude implements, they were the product of centuries of medical refinement, designed with an understanding of anatomy that wouldn't be matched again until the Renaissance. One particularly chilling discovery in the ruins of a Roman battlefield hospital revealed a collection of tools so advanced, they included a vaginal speculum almost identical to those used in gynecology today, a device that wouldn't reappear in Europe for another 1,500 years. The sophistication goes beyond craftsmanship. Roman medical texts like those by Galen and Celsus describe procedures, from cataract removal to bladder stone extraction, that required not just steady hands but deep knowledge of human physiology. Celsus even detailed a primitive form of anesthesia, recommending mandrake root and wine mixtures to dull pain during surgery. Excavated scalpels show evidence of being honed to a molecular-level sharpness, rivaling modern surgical steel. And those bone drills, they incorporated a design feature still used in orthopedics today, a central pin to prevent slipping and minimize tissue damage. This wasn't trial and error, it was systematized medicine, backed by dissections, though often on animals rather than humans, and meticulous observation. Yet by the Middle Ages, much of this knowledge had evaporated. The Dark Ages didn't just halt progress, it erased centuries of accumulated wisdom. surgical texts were burned as heresy, techniques dismissed as pagan superstition, and the very concept of sterile procedure forgotten. A 9th century European surgeon might have relied on the same rusty knife for bloodletting and amputations with predictable results. The contrast couldn't be starker. Where Roman field medics carried sterilizing kits with heated irons, medieval barber surgeons often worked in filth, unaware that cleanliness affected outcomes. What if this regression hadn't happened? Imagine a world where Roman medical knowledge continued evolving uninterrupted. Would we have mastered germ theory centuries before Pasteur, developed precision antibiotics from mold observations like those documented in ancient Greek texts? Today's surgeons are rediscovering some of these old ideas, like using silver for its antimicrobial properties, a practice Roman military doctors employed to prevent wound infections. Modern laparoscopy owes a debt to those early specula and probes, proving that good design transcends time. The real tragedy isn't just the tools we lost, but the lives that might have been saved if their wisdom hadn't been buried first by history, then by our own assumptions that older must mean primitive. In the quiet gleam of these ancient instruments lies a challenge: to honor the past not by marveling at it, but by learning from it. Imagine sailing across the North Atlantic under thick, sunless skies, no compass, no landmarks, just an endless expanse of gray. For Viking navigators, this wasn't a hypothetical challenge. It was routine, yet somehow they crossed thousands of miles with astonishing accuracy, reaching destinations like Iceland and Newfoundland centuries before Columbus. How Norse sagas speak of a mysterious tool called the Sunstone, a crystal that could reveal the sun's position even through dense fog or storm clouds. For years, historians dismissed this as myth until science caught up with legend. The key lies in a property called birefringence, found in minerals like calcite or cordierite. When light passes through these crystals, it splits into two beams, each polarized at a different angle. By rotating the stone until the intensities of these beams match, a navigator can pinpoint the sun's location with eerie precision, even when it's completely hidden. Modern experiments prove it works. In 2011, researchers using a calcite sunstone on overcast days in Hungary determined the sun's position within 5 degrees, a margin small enough to guide a ship safely. The Vikings likely held these stones up to the sky, turning them slowly until the light patterns aligned, then using shadow sticks or dials to confirm direction. But here's the twist: this wasn't just clever physics. It was part of a larger navigational toolkit that blended observation, intuition, and technology. Viking sagas also mention horizon boards, wooden slabs with notches to track the sun's arc, and bearing dials that may have used magnetic lodestones. Together, these tools formed a system as sophisticated as any modern instrument panel, just one built from stone, wood, and keen perception. Recent underwater discoveries add weight to the theory. A calcite crystal found in a 16th century shipwreck off the Channel Islands, though later than the Viking Age, shows the technique's staying power. Could sunstones have a place in today's world? Surprisingly, yes. While GPS dominates navigation, it's vulnerable to solar flares, hacking, or simple battery failure. Polarizing crystals offer a fail-safe, requiring no power or satellites. Aerospace engineers have even tested them as backup systems for aircraft, and hikers could carry lightweight versions as emergency tools. The deeper lesson, though, is about resilience. The Vikings didn't just survive harsh conditions, they thrived by adapting to them, turning natural phenomena into precision instruments. In an age of fragile tech, their sunstone whispers a reminder: sometimes the most reliable solutions aren't the most complex, but the most attuned to the world itself. While modern documents fade and digital files become unreadable as formats evolve, the Rosetta Stone stands as a silent witness to the durability of ancient ingenuity. Carved in 196 BCE, its inscriptions remain sharp and legible after 22 centuries, not because of some fluke, but thanks to a meticulously crafted carbon-based ink formula perfected by Egyptian scribes. This wasn't just pigment mixed with water. It was a sophisticated blend of soot, plant gums, and binding agents designed to withstand time itself. Modern analysis reveals nanoparticles of carbon embedded in the stone's grooves, their stability unmatched by today's synthetic dyes. The secret, a chemical harmony between organic and inorganic components, creating a film that resists oxidation, moisture, and even microbial decay. What's startling is how far we've strayed from this wisdom. Contemporary printer inks, laden with volatile organic compounds and cheap pigments, degrade within decades under normal conditions. Important historical records from the 19th century are already crumbling, their texts ghostly and unreadable, while tax documents from the 1980s fade into oblivion. Even digital storage isn't immune. Hard drives fail, cloud services shutter, and file formats become obsolete. Yet the Rosetta Stone's message endures, its clarity undiminished by the rise and fall of empires. Scientists are now reverse engineering these ancient recipes with startling results. A team at the University of Copenhagen recreated the ink using period-accurate methods, grinding soot from burnt olive pits with acacia gum and water. When applied to papyrus and aged artificially, the ink showed negligible fading compared to modern counterparts. The key lies in its simplicity. Carbon's molecular structure is inherently stable, while the plant gums act as natural fixatives, bonding the pigment to surfaces at a microscopic level. Researchers speculate that scribes may have even added traces of copper or iron salts to inhibit mold, an early form of biocide we're only now appreciating. The implications stretch far beyond museum conservation. Imagine legal documents, property records, or even cultural archives printed with these resilient formulas. Libraries could preserve knowledge for millennia without relying on fragile servers or acid-laden paper. Some startups are already experimenting with carbon-based inks for 3D printing, creating objects designed to outlast their makers. But the real revolution might be ecological. Unlike petroleum-based inks, these ancient recipes are non-toxic and biodegradable, offering a sustainable alternative to an industry drowning in chemical waste. Yet the deeper question lingers: why did we abandon such effective technology? Part of the answer lies in the Industrial Revolution's demand for speed and scale. Carbon inks require time-consuming preparation, while modern alternatives dry quickly and flow through printers effortlessly. But in our pursuit of convenience, we sacrificed permanence. The Rosetta Stone challenges that trade-off, proving that durability and craftsmanship aren't relics of the past, but guideposts for the future. As we grapple with digital fragility and environmental costs, its stubborn ink whispers a lesson. Sometimes progress means looking backward to move forward. Amid the bustling canals of Tenochtitlan, the Aztec capital that would later become Mexico City, an agricultural marvel flourished, one that turned swampland into a breadbasket capable of feeding hundreds of thousands. These weren't ordinary fields, but Chinampas, artificial islands woven from reeds, stakes, and layers of nutrient-rich lake mud, floating like emerald ribbons across the water's surface. Picture a grid of fertile plots, some no wider than a suburban backyard, each producing up to 7 harvests per year through a symphony of hydroponics, companion planting, and crop rotation, all without synthetic fertilizers or heavy machinery. While modern agriculture guzzles water and depletes soil, the Chinampas system achieved something extraordinary: sustainability at scale, nourishing an empire while enriching its ecosystem. The genius of Chinampas lay in their closed-loop design. Willow trees planted along the edges anchored the islands with their roots while providing shade to regulate water temperature. Between crops, farmers dredged nutrient-dense muck from the canal bottoms, replenishing the soil naturally. Aquatic plants like water hyacinth filtered impurities, creating habitats for fish that in turn fertilized the water with their waste, a perfect symbiosis. Maize grew tall alongside beans that fixed nitrogen in the soil, while squash vines shaded out weeds, mimicking nature's own layered productivity. Archaeologists estimate a single acre of Chinampa could feed 20 people annually, outperforming medieval European farms by a factor of 10. Today, as climate change threatens global food security, researchers are asking, could this ancient system offer solutions? In Xochimilco, remnants of the original Chinampas still operate, yielding bumper crops of organic vegetables with minimal carbon footprint. Scientists from the Universidad Autónoma Metropolitana found these plots retain moisture 20% longer than conventional farms during droughts, thanks to the surrounding water buffer. Even more striking, their biodiversity rivals natural wetlands, hosting endangered species like the axolotl salamander. Modern adaptations are already emerging. Floating farms in Bangladesh grow rice and greens on riverbeds, while Singapore's rooftop aquaponics borrow the Aztec principle of stacking ecosystems. Yet reviving Chinampas fully requires more than nostalgia. It demands rethinking our relationship with land and labor. These gardens thrived on intimate knowledge passed through generations, with farmers reading water levels and soil textures like a language. Scaling that wisdom to feed millions today would mean valuing slow expertise over industrial speed. But the payoff could be transformative. Imagine cities ringed by productive wetlands, where food grows without draining rivers or eroding topsoil. The Chinampas' legacy isn't just about the past, it's a challenge to build a future where abundance doesn't come at the Earth's expense. In their quiet, floating rows lies a radical idea that the best way forward might be to root ourselves in deeper traditions. Beneath the marble floors of the Temple of Artemis at Ephesus, one of the ancient world's wonders, ran a network of clay pipes so advanced it would take centuries for the modern world to catch up. This wasn't just plumbing, it was a fully functional central heating system, circulating warm air through hollow spaces in the walls and under the floors, creating a comfortable environment even in the depths of winter. The Greeks called it a hypocaust, and its principles were so effective that the Romans later adopted and expanded the technology across their empire, from bathhouses to villas. But here's what's astonishing. While we associate radiant heating with modern luxury, the engineers of Ephesus were mastering it over 2,000 years ago, using nothing more than clay, fire, and a profound understanding of airflow. The mechanics were deceptively simple yet brilliant. A furnace burned wood or charcoal in a basement chamber, heating the air above it. As the warm air rose, it traveled through the hollow channels embedded in the floors and walls, radiating heat evenly throughout the space before escaping through vents in the roof. The thick clay pipes and tile floors acted as thermal batteries, holding heat long after the fire died down. Even the spacing of the channels was meticulously calculated. Too close, and the floors would scorch; too far apart, and the heat would dissipate unevenly. This wasn't guesswork, it was thermodynamics in action, refined through trial and observation. Yet by the Middle Ages, this knowledge had all but vanished in Europe. The collapse of the Roman Empire and the ensuing chaos disrupted the trade networks and skilled labor needed to maintain such systems. Hypocausts became relics, their broken tiles repurposed for simpler buildings. But in the eastern reaches of the Byzantine Empire, traces of the technology lingered. The Great Palace of Constantinople reportedly used a version of the system well into the medieval period, proving its longevity when preserved. So why did it disappear elsewhere? The answer lies in a perfect storm of factors: the cost of fuel, the rise of smaller, more decentralized living spaces, and a cultural shift away from communal bathing, a cornerstone of Roman life that had driven much of the demand for hypocausts. Today, as we grapple with energy crises and carbon footprints, engineers are revisiting this ancient approach with fresh eyes. Modern radiant floor heating, though powered by electricity or hydronic tubing, operates on the same basic principle as the hypocaust. But the original design holds untapped advantages. Clay, unlike metal or plastic, is abundant, sustainable, and retains heat far more efficiently. Some architects are experimenting with passive solar hypocaust-inspired systems, pairing thermal mass with renewable energy to create buildings that stay warm with minimal power. In Turkey, researchers have even reconstructed working hypocausts using traditional materials, finding they can maintain comfortable temperatures with 30% less energy than conventional heating. The real lesson of Ephesus' hidden pipes isn't just about technology, it's about mindset. The Greeks and Romans didn't just heat buildings, they designed them in harmony with natural forces, leveraging physics rather than fighting it. In an age of gas-guzzling furnaces and fragile supply chains, their example whispers a challenge. What if the greenest solutions aren't the ones we invent, but the ones we remember? The hypocaust didn't fade because it failed. It faded because we forgot how to listen to the wisdom in the walls. Long before modern hospitals or sterile operating rooms, an Indian physician named Susruta was performing intricate surgeries that would make even today's medical students marvel. In the 6th century BCE, his groundbreaking text, the Susruta Samhita, documented procedures so advanced they wouldn't become commonplace in the West for over 2 millennia. Picture this: a patient with a severed nose, a common punishment for criminals in ancient India, lying still as Susruta's team carefully sliced a flap of skin from the forehead, twisted it into place, and sculpted a new nasal passage using hollow reeds to maintain airflow during healing. This wasn't just primitive trial and error. It was precise, systematic plastic surgery, complete with detailed instructions on anesthesia, wound care, and minimizing scarring. What sets Susruta apart isn't just the complexity of his techniques, but the scientific rigor behind them. His texts describe over 120 surgical instruments, many resembling modern scalpels, forceps, and probes, all crafted from bronze and sharpened to a fine edge. He advocated sterilizing tools with hot water and herbal antiseptics, a rudimentary but effective infection control method, and even outlined the ideal qualities of surgical thread, recommending materials that would dissolve naturally as wounds healed. His skin graft methods, which involved transferring healthy tissue to burned or injured areas, laid the foundation for today's reconstructive surgeries. But perhaps most astonishing was his understanding of anatomy. Without formal cadavers to dissect, Susruta had students practice incisions on gourds and dead animals, developing a tactile familiarity with human tissue that rivaled Renaissance anatomists. Yet for all its brilliance, much of this knowledge slipped into obscurity. As Indian medical traditions fragmented and foreign invasions disrupted scholarly networks, Susruta's texts were preserved but rarely practiced at their original level of sophistication. When British colonizers encountered these manuscripts in the 18th century, they initially dismissed them as myth until surgeons like Joseph Carpue adapted the ancient rhinoplasty techniques, rebranding them as the Indian method in European medical circles. The irony is palpable. What was once common practice in Varanasi became a novelty in London, stripped of its cultural origins. Today, historians and surgeons are reassessing Susruta's legacy with fresh eyes. His emphasis on minimally invasive procedures and natural healing aligns strikingly with modern, precision medicine, while his herbal antiseptics foreshadowed the antibiotic resistance crisis by advocating alternatives to chemical sterilization. Some researchers are even revisiting his descriptions of mama points, a vital energy centers similar to acupuncture nodes, to explore their potential in pain management. The real tragedy isn't that Susruta's techniques were lost, but that they were sidelined for centuries, delaying medical progress out of cultural bias. In an era where we're racing to develop robotic surgeons and AI diagnostics, his work whispers a timeless lesson. Sometimes the future of medicine isn't just about inventing new tools, but remembering old wisdom. While modern highways crumble after a few harsh winters, the Apian Way, Rome's legendary Queen of Roads, still bears the grooves of chariot wheels after 2,000 years. This isn't luck, it's the result of engineering so meticulous, it puts many of our asphalt ribbons to shame. Roman roads weren't just dirt paths or cobblestone stretches, they were multi-layered masterpieces designed to outlast empires. Picture a cross-section. At the base, large stones set in mortar formed a sturdy foundation, followed by layers of gravel, sand, and crushed tile, each compacted to perfection. The crowning touch, carefully fitted volcanic rock slabs, angled slightly outward in a cambered curve that sent rainwater cascading into drainage ditches instead of pooling and eroding the surface. This wasn't just construction, it was infrastructure as philosophy, built with the unwavering belief that greatness demanded permanence. The genius of these roads lay in their adaptability. Romans didn't impose one rigid design, they tailored each route to its environment. In marshy areas, they drove oak pilings deep into the ground to stabilize the roadbed. Mountain passes featured switchbacks and retaining walls, while desert stretches used local materials like flint or basalt. Modern core samples from ancient British roads reveal up to 15 distinct layers, some containing lime mortar with self-healing properties similar to Roman concrete. And those famous straightaways, surveyors achieved near-perfect alignment using simple but effective tools like the groma, a cross-shaped device that helped plot right angles, and chorobates, a water level so precise it could detect gradients as slight as 1 part in 500. Yet for all their sophistication, Roman roads didn't rely on exotic materials. They used what was locally available: volcanic rock near Pompeii, flint in Britain, even recycled pottery shards as aggregate. This sustainability stands in stark contrast to today's reliance on energy-intensive asphalt, which requires constant resurfacing and emits tons of carbon dioxide during production. Engineers at the University of California recently modeled Roman road durability, finding that their layered design distributes weight so efficiently, it reduces surface stress by up to 40% compared to modern pavements. Some European towns, like parts of Portugal, still use original Roman roadbeds for light traffic, a testament to their endurance. So why don't we build like this anymore? The answer lies in the clash between short-term economics and long-term vision. Roman roads took years, sometimes decades, to complete, with costs borne by an empire that valued legacy over quick returns. Today's infrastructure projects face tight budgets and even tighter deadlines, prioritizing speed over longevity. But as potholes cost drivers billions annually and climate change stresses aging pavement, some regions are experimenting with Roman-inspired solutions. The Netherlands has incorporated self-healing bacteria into concrete roads, while Scotland's A9 highway uses a multi-layer base reminiscent of the Apian Way. The real lesson of Roman roads isn't about copying their techniques verbatim, but embracing their mindset. They built not for the next election cycle, but for the next millennium. In an era where disposable has become the norm, their silent stones ask a provocative question. What if true progress isn't measured by how fast we build, but by how long it lasts? While modern farmers rely on GPS-guided tractors to plant perfect rows, ancient Chinese agriculturalists were achieving similar precision over 2,000 years ago with a deceptively simple tool, the seed drill. Unearthed artifacts and Han Dynasty texts reveal these ingenious devices as early as the 2nd century BCE, long before Europe's so-called agricultural revolution of the 16th century. Picture a wooden cart with a funnel-shaped hopper, its hollow tubes calibrated to drop seeds at precise intervals as oxen pulled it forward. But here's the twist: it wasn't just about mechanics. These drills incorporated an understanding of soil science that still impresses agronomists today. The seeds fell into shallow furrows at optimal depth, spaced to prevent overcrowding, while a trailing blade covered them with just the right amount of earth. No wasted seed, no guesswork, just consistent, abundant harvests. What set Chinese seed drills apart was their adaptability. Farmers adjusted the spacing between tubes for different crops. Millet required tighter intervals than wheat, while soybeans needed deeper placement. Some models even included a compartment for fertilizer, mixing manure or compost directly into the soil as seeds were planted. This wasn't just planting, it was an integrated system that maximized every inch of arable land. Historical records from the Song dynasty boast yields double those of medieval European farms, all while conserving precious seed stocks. The implications were profound. Reliable harvests meant stable populations, thriving cities, and even surplus grain for trade, a foundation for empire building. Fast forward to today, and our industrial-scale farming faces crises these ancient tools might help solve. Modern monoculture relies on broadcasting seeds or single-row planters, leading to uneven growth and soil depletion. Overplanting wastes resources, while underplanting leaves fields vulnerable to weeds. But researchers at China Agricultural University have found that reviving the multi-tube seed drill concept could reduce seed waste by up to 40% in smallholder farms, a game-changer for regions facing food insecurity. Even more compelling are environmental benefits. Traditional drills required no fossil fuels, compacted soil less than heavy machinery, and their precision reduced the need for chemical herbicides. The real innovation, though, lies in the philosophy behind the design. Ancient Chinese agriculture viewed fields as interconnected ecosystems, not production lines. Farmers rotated crops to replenish nitrogen, planted nitrogen-fixing beans between rows, and used pest-repelling herbs, all practices modern permaculture is now rediscovering. A seed drill wasn't just a tool, it was part of a holistic approach that sustained fertility for generations. As climate change forces us to rethink industrial agriculture's excesses, these forgotten devices whisper a radical idea: that abundance doesn't require brute force but harmony. Could adapting these ancient principles address today's challenges? Projects in rural India and sub-Saharan Africa suggest yes. NGOs have introduced simplified, bamboo versions of the drills, empowering farmers without access to tractors. The results: higher yields, lower costs, and unexpectedly renewed interest in heirloom crop varieties that thrive under low input conditions. Meanwhile, engineers in Germany are experimenting with solar-powered robotic planters inspired by the drill's multi-tube design, proving that 2,000-year-old wisdom can coexist with cutting-edge tech. The lesson here isn't about nostalgia for the past, but recognizing patterns of resilience. Chinese seed drills didn't just plant seeds, they planted ideas about efficiency, sustainability, and respect for natural systems. In an era of climate uncertainty and soil degradation, their quiet brilliance challenges us to ask, what other solutions might be hiding in the furrows of history, waiting to be unearthed and adapted for a hungry future? Herodotus once described something that baffled historians for centuries: massive Egyptian barges built not from timber, but from a concrete-like material that floated effortlessly on the Nile. At first glance, the idea seems impossible. Concrete sinks, right? Yet recent experiments by materials scientists have revealed a startling truth. The ancients may have mastered a lightweight, waterproof formula that could revolutionize how we think about shipbuilding today. The key lies in an ingenious blend of local ingredients. Unlike modern concrete, dense with Portland cement, Egyptian floating stone likely mixed volcanic ash from the deserts with lime and organic fibers like papyrus or straw. This created a porous, buoyant matrix light enough to stay afloat yet strong enough to withstand river currents. Texts from the reign of Pharaoh Sneferu describe cargo vessels hauling hundreds of tons of limestone blocks using this very method. When a team from the University of Cairo recreated the recipe in 2019, their prototype supported over 200 kilograms without sinking, even after weeks submerged. The secret, tiny air pockets trapped within the material, acting like natural flotation chambers. But why would a civilization surrounded by forests of acacia and sycamore bother with concrete boats? The answer reveals a deeper wisdom. Egypt's woodlands were precious and slow-growing, reserved for sacred objects and elite construction. By turning to mineral-based materials, they conserved scarce resources while tapping into an abundant local supply of lime and ash. Even more remarkably, these barges were reportedly self-repairing. When cracks formed, Nile water interacted with the mixture to form new mineral deposits, sealing gaps, a property modern engineers are now racing to replicate in living concrete infused with bacteria. The environmental implications for today are staggering. Modern shipping accounts for nearly 3% of global carbon emissions, with steel-hulled freighters requiring constant maintenance and fossil fuels. Imagine cargo vessels built from mineral composites that heal themselves, require no deforestation, and could be recycled into new structures at the end of their lifespan. Startups in Norway and Japan are already testing similar concepts, blending ancient principles with modern aerogels to create ultra-light, durable hulls. One experimental design even incorporates crushed date palm fibers, a direct nod to Egyptian methods, to enhance flexibility and reduce cracking. Beyond practicality, these concrete boats hint at a lost philosophy of material science. The Egyptians didn't just use what nature provided, they collaborated with it, designing materials that worked in harmony with their environment. In an era of microplastics choking our oceans and shipbreaking yards poisoning coastlines, their approach feels less like a relic and more like a roadmap. The next wave of green shipping might not emerge from a Silicon Valley lab, but from the whispers of papyrus scrolls where the Nile's ancient engineers wrote the first draft of a sustainable future. While modern trigonometry relies on angles and sine waves, Babylonian mathematicians took a radically different path, one etched into clay tablets over 3,000 years ago. Discovered in the ruins of ancient Mesopotamia, these tablets reveal a system so advanced it could calculate the positions of Jupiter's moons and the dimensions of temples with uncanny precision. But here's what stuns historians: they did it all without ever mentioning degrees or right triangles. Instead, they used a concept called reciprocal ratios, focusing purely on the relationships between numbers. Picture a tablet labeled Plimpton 322. its cuneiform script detailing a table of perfect Pythagorean triples whole numbers that satisfy the famous a 2 plus b2 equals c2 theorem centuries before Pythagoras was even born. The brilliance of their method lies in its simplicity, where we might use sine or cosine functions to model a ramp's incline. Babylonian scribes worked with base 60 fractions, breaking problems into proportional steps. Need to measure the height of a ziggurat, they'd compare the shadow cast by a known object, then scale it up using fixed ratios. This wasn't just arithmetic, it was a computational framework optimized for the real-world challenges of their time, surveying land, tracking stars, or designing irrigation canals. Modern mathematicians have confirmed these tables could achieve accuracy within 1%, rivaling handheld calculators. So why does this matter today? Our angle-based trigonometry, while powerful, can be cumbersome for certain applications. Engineers modeling sound waves or stock market fluctuations often convert angles into ratios anyway, a step the Babylonians skipped entirely. Researchers at the University of New South Wales have found that adapting their reciprocal approach could streamline algorithms in fields like computer graphics, where rapid calculations are critical. Even GPS systems, which rely on triangulation, might benefit from a ratio-first mindset to reduce processing steps, but the deeper revelation is cultural. The Babylonians didn't separate math from daily life. Their tablets mix astronomical data with grain quotas and loan interest, revealing a worldview where numbers served practical harmony. In an era drowning in abstract equations, their clay tablets whisper a radical idea that the most elegant math isn't about complexity but clarity. Perhaps the next breakthrough won't come from inventing new symbols, but from rediscovering old ways of seeing. While Byzantine ships terrorized enemies with their naval flamethrowers, ground troops carried a more compact horror handheld clay grenades filled with the infamous Greek fire. Archaeologists excavating battle sites near Constantinople have unearthed these fist-sized terracotta spheres, their interiors still stained with mysterious residues. Unlike the liquid sprayed from ships, these grenades contained a thickened formula designed to adhere to targets and burn longer, a medieval version of napalm. One particularly well-preserved specimen, discovered in a 12th century armory in Bulgaria, revealed traces of pine resin, sulfur, and something unexpected: traces of quicklime mixed with an organic binder, possibly animal fat. When ignited, this combination wouldn't just burn, it would explode on impact, scattering sticky flames in all directions. Modern chemists analyzing these remnants have stumbled onto properties that defy expectations. The pine resin acted as both fuel and adhesive, while the quicklime generated intense heat when reacting with moisture, even human sweat. But it's the sulfur's role that intrigues researchers most. When burned with certain organic compounds, it forms sulfuric acid aerosols, creating a secondary choking effect similar to modern tear gas. This wasn't just a weapon of fire, it was a multi-layered assault on the senses, designed to panic as much as maim. Recreations at the University of Athens confirmed the grenades could sustain flames at over 800 degrees Celsius for nearly 10 minutes, enough to melt through leather armor or ignite wooden siege engines. What's startling is how these ancient mixtures parallel contemporary chemical engineering. The same sulfur compounds that made Greek fire so terrifying are now used in industrial catalysts and battery technologies. Quicklime's exothermic properties power modern self-heating meals for military rations. Even the pine resin's adhesive qualities have inspired bio-based glues for medical sutures. A team at MIT recently patented a flame-retardant coating derived from similar resin formulations. proving that destructive innovation can sometimes be repurposed for protection. Yet the grenade's true legacy might lie in their delivery system. Their ceramic casings were engineered to fracture predictably, maximizing splash damage without premature detonation, a principle echoed in today's fragmentation grenades. Some specimens show scoring marks, suggesting soldiers could adjust break patterns by carving the clay before firing. This level of customization hints at a sophistication we rarely associate with medieval warfare. As drones and smart munitions dominate modern battlefields, these ancient grenades whisper a provocative thought. Sometimes, the most advanced solutions aren't about new materials, but perfecting the art of controlled destruction. The irony is palpable. Byzantine chemists crafted these weapons to defend an empire long gone, never imagining their secrets might one day heal instead of harm. In their cracked clay shells lies a challenge: to mine the past not for better ways to fight, but for forgotten wisdom that could light a different kind of fire, one that drives progress rather than destruction. High above raging Andean rivers, the Incas built bridges that defied both gravity and time, suspended pathways woven entirely from grass, stronger than the iron bridges of Renaissance Europe and flexible enough to sway with earthquakes. These weren't crude rope crossings, but engineering marvels like the Quipus, a 100-foot span that still connects mountain villages today, rebuilt annually using techniques unchanged for 600 years. Picture teams of artisans twisting iku grass into slender cords, then braiding those into cables thicker than a man's thigh. Layer by layer, they created structures capable of supporting llama caravans, soldiers, even Spanish conquistadors in full armor, all without a single nail or metal beam. The secret lay in the Incas' intimate understanding of materials. They selected specific highland grasses for their tensile strength, drying and combing them until the fibers could be twisted into ropes that rivaled steel. 3 massive cables formed the bridge's backbone, 2 as handrails, and 1 as the walking surface, while smaller ropes crisscrossed beneath like a spiderweb, distributing weight evenly. When winds howled or tremors shook the mountains, the bridges didn't resist the forces but absorbed them, swaying harmlessly where rigid European designs would have shattered. Modern engineers have calculated that the cable's natural elasticity allowed them to stretch up to 5% under load, a feature modern suspension bridges only achieved centuries later with steel alloys. What's most astonishing is how these bridges were maintained. Unlike permanent stone structures, the Incas embraced impermanence as a strength. Every year, communities gathered to renew the Quipus in a 3-day festival, dismantling the old bridge while weaving its replacement. This wasn't just practicality, it was a living tradition that passed engineering knowledge between generations. The process itself became a stress test. If a cable snapped during construction, it happened on the ground, not mid-river. Compare that to modern infrastructure, where inspection crews often miss hidden corrosion until a catastrophic failure occurs. Today, as climate change intensifies floods and earthquakes, civil engineers are studying these ancient designs for solutions. The Golden Gate Bridge's chief engineer even cited Inca principles when designing its flexibility to withstand Pacific storms. Researchers at Peru's Universidad Nacional de Ingeniería have created synthetic fiber cables mimicking grass's energy-dispersing properties, ideal for disaster-prone regions. Meanwhile, in Nepal, post-earthquake rebuilding projects have incorporated woven bamboo bridges inspired by Andean models, lighter, cheaper, and more resilient than concrete alternatives. But the real lesson isn't just about materials, it's about mindset. The Incas didn't conquer nature, they collaborated with it, using renewable resources and community labor to create infrastructure that adapted rather than dominated. In an age of brittle steel and carbon-intensive concrete, their grass bridges whisper a provocative question. What if the future of resilient design isn't stronger materials, but smarter relationships with the forces we're trying to withstand? In the heart of Persia's scorching deserts, where summer temperatures could melt lead, engineers built something extraordinary: gigantic, dome-shaped structures called yakchuls, capable of storing ice even in the fiercest heat. These weren't just primitive cellars, they were masterpieces of passive cooling, designed with a precision that modern architects are only now fully appreciating. Picture a towering conical structure, its thick mud brick walls rising high above the sand, connected to a labyrinth of underground channels and shaded pools. Inside, even at the height of summer, temperatures could plunge below freezing, all without a single watt of electricity or a drop of refrigerant. The secret lay in a combination of ingenious design and natural physics. The yakchul's walls, sometimes over 6 feet thick, were made from a special mortar called saruj, a mixture of clay, sand, ash, and goat hair that acted as a superb insulator. Beneath them, qanats, or underground aqueducts, channeled cool water from distant mountains, while cleverly placed windcatchers funneled nighttime breezes downward into subterranean storage chambers. During winter, workers diverted water into shallow basins where the desert's frigid nights froze it into sheets of ice. These were then broken up, packed with insulating straw, and stacked inside the yakchuls, where they'd slowly melt over months, providing chilled water and even ice cream for Persian nobility well into the summer. What's astonishing is how these structures harnessed every trick of thermodynamics long before the science had a name. The domed shape minimized surface area exposed to the sun, while the light-colored exterior reflected solar radiation. Underground, the Earth's natural thermal inertia, the way soil maintains a relatively constant temperature below the surface, acted like a giant heat sink. Even the orientation mattered. Many yakchuls were aligned to capture prevailing winds, which, as they passed over subterranean water channels, created evaporative cooling effects similar to modern swamp coolers. Modern thermal imaging studies of surviving yakchuls in Iran's Yazd province show temperature differentials of over 50 degrees Fahrenheit between the interior and the outside air, a performance that rivals many modern refrigerators. Today, as global energy demands skyrocket and air conditioning accounts for nearly 10% of worldwide electricity use, engineers are mining these ancient designs for sustainable solutions. Researchers at the University of Tehran have modeled yakchul's thermal properties, discovering that their passive systems could reduce cooling energy needs by up to 80% in arid climates. Architects from Arizona to Australia are experimenting with updated versions, combining traditional mud brick insulation with modern materials like aerogel to create ultra-efficient cold storage for vaccines and perishable goods in off-grid areas. One project in Rajasthan, India, uses a yakchul-inspired structure to preserve farmers' crops without refrigeration, cutting post-harvest losses by almost half. Yet the real lesson of the yakchuls isn't just about technology, it's about rethinking our relationship with the environment, where modern AC units fight nature by blasting chilled air into sealed boxes. The Persian approach worked in harmony with natural cycles, using the desert's own temperature swings as a resource. In an era of climate crisis, that philosophy feels revolutionary. What if, instead of building energy-guzzling systems to dominate our surroundings, we designed spaces that listen to them? The yakchuls stand as silent witnesses to a time when innovation wasn't about conquering nature, but collaborating with it, a reminder that sometimes the greenest solutions aren't invented, but remembered. From self-repairing concrete that outlasts modern infrastructure to windcatchers that cool buildings without electricity, these 29 forgotten innovations reveal a startling truth: our ancestors weren't just clever, they were visionary. Their solutions emerged from constraints we've long forgotten. No fossil fuels, no microchips, no global supply chains. Yet somehow, they crafted technologies that balanced efficiency with sustainability in ways we're still struggling to replicate. The Roman architect Vitruvius once wrote that great design harmonizes strength, utility, and beauty principles etched into every artifact we've explored, from the precision of the Antikythera Mechanism to the resilient simplicity of Inca grass bridges. What's most humbling isn't just the ingenuity of these creations, but how many were lost to the turbulence of history. The Library of Alexandria's burning erased countless scrolls, while wars and plagues severed chains of apprenticeship that passed down irreplaceable skills. Other innovations, like Hero's steam engine, simply lacked the right societal conditions to flourish, proof that progress isn't inevitable. Yet in their fragments, these technologies whisper an urgent lesson: human brilliance is fragile. Without deliberate preservation, even the most transformative ideas can vanish like footprints in sand. This isn't about romanticizing the past or rejecting modernity. It's about recognizing that innovation isn't linear. Sometimes it loops back, rediscovering old wisdom through new lenses. Today's scientists studying Roman concrete or Chinese seed drills aren't copying ancient blueprints. They're having conversations across time, blending millennia-old insights with cutting-edge tools. The Yakchuls of Persia and the Hypocausts of Rome remind us that sustainability isn't a 21st century invention, it's a rediscovery. As climate change, resource scarcity, and infrastructure decay challenge our world, history offers more than nostalgia, it provides a toolkit. Imagine cities where buildings heal their own cracks like the Pantheon, or agricultural systems as productive as Chinampas without draining aquifers. Picture medical implants with the lifelong durability of Damascus steel, or solar arrays as elegantly simple as Archimedes mirrors. The solutions we need might not require inventing something unprecedented, but reviving what already worked, then refining it with modern knowledge. Which of these ancient marvels resonates with you? Is it the quiet genius of the Baghdad battery, hinting at forgotten energy systems, or perhaps the Maya's celestial math, proving that civilization isn't measured by silicon but by curiosity? Drop your thoughts below. We're endlessly fascinated by how the past can illuminate the future. And if you've enjoyed this journey through history's hidden innovations, consider subscribing. Together, we'll keep unearthing the ideas that time forgot, but the future desperately needs. After all, the next chapter of human progress might not be written in a lab, but in the echoes of what came